Good afternoon, bon après-midi. Welcome to this edition of the Physical Society Colloquium. I'm coming to you live from the brutalist majesty of the Rutherford Physics Building at McGill University in beautiful downtown Montreal, where the bandwidth is as high as the Gaia Space Observatory. If you are in the Zoom session and you prefer not to be recorded or live streamed, please log out of Zoom and join us via YouTube. This afternoon, we will have a 45-minute talk followed by 15 minutes of questions and answers. To ask a question in Zoom, please use the raise hand feature following the talk. To ask a question in YouTube, please enter it into the chat. The questions will be relayed to me by my sidekick following the talk. After the Q&A session, the live stream and recording will stop. Professors will be asked to log out of the Zoom session, and undergrads, grads, and postdocs, as well as any other non-faculty in the Zoom session, will be invited to the après colloque, a chance to get to know the speaker better. With that, I will now pass to Professor Daryl Haggard to introduce the speaker. Daryl.
Thank you so much and welcome everybody. It's a pleasure to have everyone here and especially Kathryn Johnston, our speaker. Professor Johnston received her PhD in astronomy and astrophysics from UC Santa Cruz and her BA in mathematics from Cambridge University. She was a postdoctoral member of the Institute for Advanced Study at Princeton University and an assistant professor at Wesleyan University before joining the astronomy faculty at Columbia University in 2006. She did the heavy lift there of being department chair for several years. And so we all thank her for that incredible amount of service. Professor Johnston has been a recipient of the NSF Career Award and is currently a group leader for the Dynamics group at the Flatirons Center for Computational Astrophysics. She's also chair of Columbia's Arts and Sciences Committee on Equity and Diversity, and she shared generously a discussion about that work with our community during the lunch hour today. Professor Johnston's research interests include dynamics, galaxy formation, interaction and evolution, and stellar populations here in the Milky Way and also in our local group galaxies. And today she's going to tell us very exciting new stuff from the Gaia satellite, as Bill Koish already intimated. Kathryn, welcome very much. Thank you very much for joining us today, and take it away.
Wonderful. Thank you so much, Daryl, for the lovely introduction. And thank you, everybody, for the invitation. I'm really delighted to be here, if only virtually. And as Daryl said, I wanted to welcome you to the Milky Way, courtesy of the Gaia satellite, which has been providing some amazing new views of our galaxy over the last few years. In particular, as Daryl said, I'm a dynamicist, and this data set is a real playground for people like me for exploring the Milky Way and how things move in the Milky Way and implications for the present structure and past history. So often in these talks the last couple of years, I've been giving a review because it feels there's so many results coming out of Gaia. But today I instead thought this is actually my first virtual colloquium. And I know we've all been on Zoom a lot. So instead of trying to do a lot of things, I'm instead going to take a deep dive into one thing, just one thing that my group is thinking about. So hopefully this won't be too long and too diverse, narrow in a good way. The strength of Gaia, let me see, I'm going the wrong way. The strength of Gaia is that it measures positions on the sky extremely carefully. So this is a map of the positions of the 2 billion stars that it's measured extremely carefully on the sky, and also giving their colors as well. And it looks like an amazing high resolution photograph of the Milky Way, but it's not. It's actually a map of positions. And the dark patches you can see are the dust lanes in our galaxy, which are obscuring some of the stars. So Gaia itself, you can see in the bottom corner, is a mission from the European Space Agency. And of course, the wonderful thing about measuring positions on the sky, they actually give you two things. In one sense, they give you distances by virtue of the nature of parallax. So stars that are further away have a smaller parallax. And the amazing thing about Gaia in being able to measure positions extremely accurately means that it can measure distances further than we've ever been able to do before using this geometrical technique. And just to give you a sense here, so we've got 1 billion stars, 2 billion stars. We've got distances to them. In order to measure those distances, if you took a tennis ball and you put it on the moon, Gaia would be able to see one side of the tennis ball from the other, which is quite amazing. So as I said, Gaia is measuring, I'm doing it again, positions over time, and that gets you distances by virtue of parallax. But also it gives you tangential motion across the sky. So in the end, what you end up with is a full phase space position for stars in the Milky Way. There's only a subset of those. 10 million of the 2 billion have radial velocities as well, and they will have the full phase space position. And the other nearly 2 billion have 5 dimensions. In terms of how fast things moving across the sky Gaia can measure, or rather how slow, I like to imagine myself as a star, walking around our nearest neighboring star beyond the sun, so Proxima Centauri. So if I walked around Proxima Centauri at walking speed, Gaia would be able to measure that speed. And of course I shine extremely brightly, so it would be able to see me as well. Okay, so a very exciting thing for galactic dynamicists. And now I want to just dive straight into some exciting Gaia results to give you the context on a slightly larger scale of the thing that we've been thinking about. And as a dynamicist, I want to spend a long time talking about basic properties of orbits and the dynamical phenomenon or kinematical phenomenon of phase mixing. And then I want to go back at the end and tell you how understanding these properties and using Gaia data should be able to tell us about origins. So, starting point, 2 years ago, we're sitting in the Flatiron Institute in the Center for Computational Astrophysics. There's about 60 astrophysicists sitting there, and it's 6 a.m. on April the 26th in 2018, and we're waiting for European Space Agency to release the second Gaia data release, Gaia DR2. 6 a.m. it gets released. And these are the sorts of things that we started to be able to see with that second data release. These 3 panels, they're a revisualization, but they were actually in the paper that came out that morning at 6 a.m. from the Gaia community. And what you're seeing here, if you remember, the sun is at about 8 kpc on the x-axis here, -8, and 0 on the y-axis. The center of the galaxy is 0, 0 here. And so what you're seeing is an appreciable corner of the galaxy. Gaia has been able to map an appreciable corner of the galaxy. If you want to look at it on scale over here, the orange ring is giving you an idea of the scale of this. For the first time, we'll be able to directly map positions of stars across this volume of the galaxy. On the left-hand plot, what you're seeing is how fast the stars moving in and out from the galactic center. And what you can see is there are motions of order plus or minus 15 kilometers per second on this scale. And the thing to remember here is that on average, pre-Gaia, we thought that the stars on average shouldn't be moving at all in radius, on average, right? They each individually move at tens of kilometers per second relative to the sun. But on average, they shouldn't be moving, there shouldn't be a bulk motion. And yet this is showing you a bulk motion. This region is going out, this region is going in, this region is going out. Similarly, you can actually look perpendicular to the galactic disk, and Gaia is able to show us that the disk, instead of just having the stars go round and round in a circle and randomly up and down, there are systematic motions. In this case, going down by a few kilometers per second and then going up by a few kilometers per second. And similarly, there are deviations in the speed with which stars move around the galaxy. And they do move at hundreds of kilometers per second in the direction around the galaxy. So this view wasn't entirely unexpected. From prior hints from SDSS over the sort of 5 years before this, people had started to see signatures of this systematic motion. But it's definitely something when we were building our models of our galaxy, we had not included this scale of systematic motion. So it's of order sort of 10% deviations from an equilibrium distribution. Now, why would that be the case? Well, I think if we just think about hierarchical structure formation, how we believe galaxies form, then it's fairly obvious. So this is the end point of a simulation of the formation of a galaxy like the Milky Way, which you can see at the center here, from the Latte team. And you can see that you have the disk at the center, which we've been observing for millennia. And you also have these objects that have been harder to see, these satellite galaxies that are orbiting it. And these satellites are in the process of plunging through the galactic disk. The galactic disk is tearing these satellites apart into these beautiful streams of stars. That's something that I've studied for decades myself. But the satellites themselves are also impinging on the galactic disk. The other thing I want you to remember here is what's being visualized here from the simulation are particles that represent the stars. But of course, galaxies are dominated by huge dark matter halos, which would surround this disk on the scale about the size of the screen, and with 10 times more in the dark matter halo than in the massive stars. So actually, there's a lot going on dynamically in terms of gravitational interactions that you can't even see here. If we were to visualize the dark matter halo and the density structure in the dark matter halo in a global sense, we might see something like, we'll just have to watch this one more time. It's a hard life. Look at these beautiful shell structures forming from interactions. Okay, we'll go through again. So if we were to be able to see the dark matter halo, the picture that we've had of dark matter halos is that these should be these giant elliptical, fairly simple global structures in the form of ellipses. Let's see this one more time. Not that one, this one. But actually, if you look very carefully in the simulations, when you include things like a satellite galaxy, which would be sitting in this red knot here, you actually find, in terms of density contrast, you find these giant structures that cannot be described by simple ellipses, in the middle of these dark matter halos. So this is what you're not seeing in the simulation before. You'd actually have a dark matter halo that itself is interacting with the disk and the satellite and being distorted. And there have been hints of this distortion in some of the Gaia data too, but that's just a teaser because I'm not going to talk about that today. So if we zoom in on the disk now and we ask what's happening to the disk, this is a simulation. Still going the wrong way. I'm sorry, I'm going to get this one of these days. This is a simulation where we've zoomed in and we're just looking at high resolution at a galactic disk. There is, again, a dark matter halo here, and it's interacting with a single satellite just to get an idea. So watch as the satellite goes by. You can see the vertical waves, the disk wobbling up and down. It's really beautiful. And we actually think that this is of similar order to the sort of interaction that the Milky Way is currently undergoing with one of its satellites, the Sagittarius dwarf galaxy. This is a simulation that Shervin Laporte ran while he was a postdoc with me. It's extremely high resolution for the time, which was 2017. We have about 10 million particles in the disk in the simulation and tens of millions more in the dark matter halo. If we look at the simulation and we do projections in density looking down, early on you have a smooth disk unperturbed by the satellite because it hasn't fallen in yet. By about 6 years in, you have spiral arms and a bar forming, and this is about what we think the Milky Way roughly looks like and where the satellite would be today. If we run the simulation even further forward, you see that the disk gets much more messy as the satellite plunges further in. And at the bottom, we're color coding this by the mean vertical velocity at each point in the disk, which is close to 0 when it's unperturbed. But you can see right here, this dark blue splodge is showing you where there's an ongoing interaction with the satellite. And because the satellite is much more concentrated than the disk, the interaction is fairly localized. And we'll be taking a deep dive into this later on in the simulations. But this is to show you that the wiggles in this simulation, they're slightly more than our own galactic disk of order tens of kilometers per second. These wiggles are entirely expected as bending waves and breathing waves in our galactic disk being perturbed by a satellite. And again, some of these ideas were being explored and had been hinted at pre-Gaia. The fun thing for us was Shervin Laporte ran these simulations in 2016, 2017. This is before the second Gaia data release. And yet, if we actually look at what we see in our simulations, we see some very similar features to what we see in the Gaia data. So this top row of panels is a repeat of the Gaia data that I showed you before. And in the bottom, which I've tried to put on the same scale, is showing you similar plots in the simulations. The only way they're not in the same scale is they're not in the same scale in the color bar because the level of oscillations in the simulations is slightly higher. But you can nevertheless see that the orbit of Sagittarius has induced very similar, that we've tried to reproduce, has induced very similar spatial scales to these oscillations, even if the amplitude is slightly higher. And this was before we actually saw the data that we see in the top panel, which is really fun. And it gives you confidence in the cosmological principle that we can model the universe from just modeling the physics at home in our own galaxy. Okay, excellent. So that was sort of context. And what I wanted to do for the rest of the talk is take this dive in and have fun with orbits and phase mixing, and then talk about where some of the signatures we're seeing in the Gaia data might allow us to learn more about origins more precisely. So, orbits of the galactic disk. You probably know that stars in our galaxy, in the disk of the galaxy, move on nearly circular orbits. So here's the galactic center. Here's a group of stars at about 8 kpc, or representing several different orbits, going in basically a circle around the galaxy. And before we get to that, if you look down in this bottom panel, this is trying to show you a phase plot equivalent to that so that you can see position and motion. In other words, if you followed any one of these orbits just in the x direction, you would see the star going back and forward in x and its speed in the x direction going up and down. And so this orbit in x and y projects in a single dimension also does something that looks rather like a circle in x v x, right? So this is a way of representing something in space, but also in phase space, in velocity at the same time. If we zoom in on these orbits, there's actually 3 different orbits represented here. One in red is very, very close to circular orbits. And then there's a blue one, which is slightly more eccentric, so oscillates back and forth by just 0.1 kiloparsecs. And the green one is slightly more eccentric than that. And so we can actually also represent the oscillation not just in x and y, but in other dimensions as well. So you can actually represent the orange orbit by this black line here as the circular orbit at that radius. And you can actually think of the blue orbit as going around in a mini circle around the bigger orbit. So you can get this pattern by modeling the combination of this blue epicycle with the black orbit. And that will give you this total oscillation. And in the green case, the epicycle is just slightly bigger. So if we then look at what this means in the, I've done it again, the radial direction, you can think about the blue orbit as just oscillating gently back and forth in a small range of radii around 8 kpc. And so its radial velocity is positive as it's going out and negative as it's going in. So this is going round and round in a little epicycle in space, and it's going round and round in this plane in a little circle. And the green one is the same, but it's more eccentric, so that circle is larger, and a circular orbit in this plane just appears as a dot, right? And then you can do the same thing in Z, right? These we've oscillated in 2 dimensions, but you can also have oscillations going up and down. In this case, the green orbit is a planar orbit. It's just in the Z equals 0 plane. But the orange orbit, which looked like it was purely circular, actually has some motion in the Z direction as well. And the blue orbit also has some oscillations in the Z direction. So in terms of looking in the ZVZ space, these motions in the Z direction can also be represented by these circles. So if we put this all together, you should think of orbits in the disk of our galaxy. This is how I like to say it. Stars go round and round in the disk. They go up and down perpendicular to the disk, and then they go in and out in radius. And another way of describing this, a powerful way of describing this, we've talked about it in terms of orbits and little epicycles. More generally, we would talk about this in terms of the action associated with an orbit, which is roughly equivalent to the area that this orbit occupies, and the angle, which corresponds to what phase it is in this oscillation. So in other words, we can describe these orbits in terms of angles, actions, and how long it takes for them to go around in any single space. And those oscillations are generally described in terms of motion in azimuth, motion in radius, and motion perpendicular to the galactic disk. So that's our complete description of orbits that we're going to use. And knowing that description of orbits, we're going to be able to interpret the Gaia data in terms of classical kinematic properties such as phase mixing, and then learn about history. Before we go on, I want to give you one more sense of scale. So we've talked about the scale of orbits we're going to talk about. The sun moves at 8 kpc from the galactic center, and it moves about 200 kilometers per second around the galaxy. And then the scale of these oscillations is going to be of order tens of kilometers per second and a few hundred parsecs either way that we're going to be talking about. But let's also give you a time scale here. So we can also look at the time scale of orbits at different radii. So these colors, they happen to be the same, but they're not associated with these colors. This is the vertical orbital time period for a near circular orbit that's just oscillating gently up and down as a function of radius. So in other words, how long does it take for a star to go once around in this diagram? And I've chosen 15 kpc for reasons that will become obvious later, but the answer to that is about 200 megayears. And if you compare that for how long does it take for that star to go around the galaxy, that's about 400 megayears. And in terms of in and out, that's in between the two. Okay, so what I would usually say is any questions. I can't actually see any of you, but if you have any questions, please let our hosts know and they will interrupt. Okay, deep breath. The next thing we're going to do is, now we understand orbits, we're going to think about groups of orbits, and we're going to have fun with phase mixing. And these are the collaborators for this part of the project. It's being led by Sarul Gandhi, who is a graduate student, actually not at Columbia, she's at NYU, and Jason, Adrian, and David Hogg. David Hogg is a professor at NYU. Adrian and Jason are postdocs at the Center for Computational Astrophysics. So what is phase mixing? The classic example that most of you will have seen in a classical mechanics class, maybe, is probably being explained to you using pendula. So for example, if you have a set of pendula and you line them up initially at phi equals 0 here, that's vertically, but suppose you have a set of pendula so they all have a small spread in frequencies or a small spread in time periods. So their frequencies are 2 pi over their time periods, and they have a small spread in time periods. Then after a quarter time period, they will have oscillated up from where they're starting. After half time period, they would have come back down. And then after a full time period, they would have oscillated back up and come back down again. And what happens if you have a small spread in time periods? It takes different amounts of time to complete that full oscillation. So what this means is, even if you start with all the pendula sitting on top of each other vertically at the beginning of this experiment, you quickly find that they spread out and they end up occupying a larger and larger range in angles, or in other words, a larger range in phases, and they mix in phases. Okay? So if we represent what that looks like in one of these diagrams that we've been talking about, so now instead of plotting x and vx or r and vr, we're going to plot phi, the angle, and v phi. So just like the orbits I was telling you about, each of these pendula would go round and round one of these orbits in a given amount of time. And some would have longer time periods and some would have shorter time periods. So if you started with everything vertically here with a single phi value, and then you let the pendula go, you'll find that the ones with the shorter time periods after a quarter period are slightly further on in phase than the ones with the longer time period. In other words, they're now occupying a range of phases, which they weren't before. And if you went further on, that range of phases would get larger and larger. And that is phase mixing, right, in the pendular context. Now we're going to look at phase mixing in the case of the galaxy. So this is the same diagram we had before, talking about orbits. In this case, we were talking about a star oscillating up and down in Z, and their speed going up and down as they oscillate in Z. So in other words, for something that's going far from the plane, when it has a negative VZ, it's decreasing its distance from the plane when it starts high, and then it's going to go below the plane to a maximum distance below, and then its VZ becomes positive, and it's going to go back above the plane again. And it's going to repeat this over and over again. So this diagram should remind you of the diagram we just used to talk about phase mixing in pendulum. And the reason that this diagram has become extremely popular is because Teresa and Toja, on the day of DR2, the second data release from Gaia, took the data from Gaia, that not the large volume that we were looking at before, but a small volume around the sun. In fact, this orange splodge is a bit too large. She actually took a volume which was more like a couple of hundred parsecs around the sun, and she just plotted Z versus VZ, and this is what she found. And this was a stunning paper that came out the day after the Gaia data release, and I think it was many people's favorite Gaia plot for the next year or two, and hopefully I'm going to point it out for you, but look, there's a snail. Isn't that beautiful? So this snail is the classic signature of phase mixing. In other words, these stars have natural frequencies. The ones in the center have a smaller frequency. They oscillate faster up and down close to the Milky Way, and the ones further out oscillate up and down slowly. So if something has happened to the Milky Way that shifts those stars off from being completely random, then they move up and down systematically, but the systematic motion in the middle will be faster than the systematic motion in the edge, and you'll end up with this beautiful spiral pattern. And this is classic phase mixing in the up and down direction in the Milky Way. And of course, you'll be unsurprised to learn that there've been many papers written on this since this discovery. In Teresa's original discovery paper, she had some nice interpretations, and there's many more out there now. And this is what we're going to talk about and dig into this a little bit because it's a beautiful, physically intuitive structure that's really fun to think about. So I said, okay, for this to work, right, on average, you expect stars just to be moving randomly up and down. The fact that we see a structure here is telling you that something non-random has happened to these stars. And of course, what's something non-random that could happen to these stars? We've already seen one example. There are other hypotheses, but here's one example. Sagittarius goes plunging through the disk of the Milky Way, and it can actually cause systematic changes in velocities that are localized in space. So it could be that Sagittarius plunging through the disk of the Milky Way could set some of these stars oscillating up and down in a non-random way. So indeed, the day after the Gaia data release, with the 60 of us sitting in the Flatiron Institute, we did go home overnight, but this paper came out the next morning, and I went back into the Flatiron Institute, and Shervin was there, and I said, Shervin, look at your models. Let's see if we can find a snail. And this is what he came up with. So here's the snail coming from this data set. I'm not sure this the exact right snapshot, but this gives you the idea. He's tried to mimic what we do, what the Gaia data release did, and take a small portion of the disk after an encounter with Sagittarius and see if he could find a spiral. And indeed he did. So this is a signature. We've known about Sagittarius for a while. We've known that the disk flops up and down. if Shervin and I were extremely intelligent, well, we're very intelligent, but if we're extremely, extremely intelligent, we might have thought to look for this before the Gaia data release. But nevertheless, it's kind of fun that we found something after. But I would note something here. Did you notice that the simulation doesn't look nearly as good as the data? That's another really fun thing about Gaia. At this point, the resolution in our data set of our galaxy is higher than the highest resolution simulations we can run, which is a tremendously exciting thing. In fact, to actually make this plot, we only have 10 million particles in our fake disk here. To make this plot, Shervin actually had to look over a much larger volume than Gaia needed to in order to make its plot, which is really fun. But the consequence of that is I'm actually going to show you some higher resolution simulations later that we've cheated a little bit on, and I'll explain that when we get there. Okay, excellent. So we talked about phase mixing up and down, right? But if you remember, when we talked about orbits, there's not just one dimension where you've got frequencies. You've also got the frequency going round, and I also said in and out. Stars go round and round, up and down, and in and out in radius. So you can actually phase mix in all three dimensions. I'll only talk about two today. We've done the phase mixing up and down and seen the signature of that. But what about the phase mixing round and round, right? What's going on there? In other words, right, we look at these stars. This is what we see in Gaia, much prettier than what we actually see in the simulations. But look at them in the XY plane, right? The galaxy in this visualization is rotating this way. We've got a set of stars here. Where did those stars come from? If we think about the orbits we described, say there's a star here, maybe it's actually on an orbit that has a little epicycle, which is going round on a circular orbit. The epicycle is circulating around on a circular orbit that actually has a radius that's slightly smaller than the patch where the star currently is. And then, what about a star that's exactly on a circular orbit in this orange patch? Say this star on the exactly circular orbit was here a while ago, half an orbit ago. This is where the orange patch, the stars on that circular orbit would be. However, this would be where the red star would be, because its orbit is actually going at a higher frequency around the galactic center. So in the time it's taken the orange star to go half an orbit from here to here, the red star has gone slightly more than half an orbit. This again is phase mixing, but now we're doing it backwards, phase mixing backwards. So in other words, in a way, we're let's see, we've got some phases here that are aligned, and as we go backwards, they become unaligned. We can do the same for a blue star. This time we pretend it's on an orbit with a slightly larger, these are called guiding radii. So this blue circular orbit is the guiding radius orbit of this blue star with the little epicycle. And that would not have gone as far an angle back in azimuth as the orange star. Okay, so where does this leave us? Let's start putting this together. If you think about all the stars that are in this volume here, even though they're in a small volume around the sun today, in the past, they would have spread out a significant fraction across the galactic disk. Okay, excellent. So we've talked about context, we've talked about orbits, we've talked about phase mixing. Let's talk about origins. And before I start putting the phase mixing pieces all together, what I want to do is talk about mechanism. Let's think about what's happening when Sagittarius dives through the galactic disk. So what I'm going to tell you is a toy model for how stars get affected. And I want to tell you right up front that this toy model is incorrect for reasons I will explain. I mean, it's pretty obvious when I say we're going to do a toy model for stars moving exactly in the plane on circular orbits. We know that that's not true, but nevertheless, it helps with thinking about intuition. So here we have a red star in the toy model, and it's coming up. Oh, no, let's start again. We have three stars in our toy model. We have a red star, a kind of yellow star, and a blue star, and they're all on the same circular orbit, but at slightly different phases. The yellow star happens to be exactly on line with the galactic center and Sagittarius at the point when Sagittarius goes through the disk. The red star is slightly lagging, and the blue star is slightly ahead. So what you should think about for this yellow star, As it comes around here, Sagittarius is above the disk and it's being pulled up. Then Sagittarius goes through the disk and it's being pulled down. And so on average, this yellow star feels an acceleration up and an acceleration down that are equal and opposite. So here's an acceleration up and an acceleration down that are equal and opposite. So if that was the only effect, you would get no net effect on the yellow star. On the red star, on the other hand, as Sagittarius is coming towards it, it's being pulled up, but it's actually getting closer to Sagittarius. It's closer to Sagittarius when Sagittarius is below the disk. So it has a small acceleration ahead and a large acceleration afterwards. So on average, it gets pulled down, and the blue star is opposite. So we can actually draw our expectation for this model, which I'm telling you is wrong. This is the sort of pattern we might expect to see in the galactic disk if our model could work in exactly the way I just said. You would see systematic changes in velocity, mean velocity across the galactic disk, and it's these sort of systematic changes that can set off the phase spiral. Now, if we look in the simulations, and what we actually did is we reran simulations very like the ones Sherwin had run, but this time with 200 million particles in them, so we could resolve both the disk and the snails, the phase spirals we want to look at. If we actually look during an encounter from minus 80 megayears to plus 120 megayears, and Sagittarius is plunging through the disk at this point, you can see Sagittarius, let me see, it's coming up through the disk, it's coming from below. So Sagittarius is initially pulling the disk down, and then it plunges through the disk and it pulls it up. But you never quite see the same pattern in the idealized model. And the reason is basically because, remember, those stars are going up and down, and they take about 200 megayears, this is at 15 kpc, to go up and down once. And that's comparable to the actual scale of the interaction. So we can't ignore how long it takes a star to go up and down in order to make this calculation. So the simple model doesn't quite work, but it nevertheless gives you an intuition as to why you get these very systematic changes in vertical velocity, even when you've got something from above and going below, where you might expect the force to average out. So where this leaves us is with this model. We've got phase mixing vertically. We've also got phase mixing horizontally. So that means that stars in local surveys actually come from a significant fraction across the galactic disk in the past. In terms of a mechanism, when something like Sagittarius plunges through the disk, this toy model isn't exactly correct, but it gives you the idea. You actually see systematic changes in velocity up and down that are different across different parts of the disk. So in other words, these stars that you're seeing in the phase spiral will have experienced different accelerations as they go across the galactic disk. And the question is, what can we do with that information and what can we learn from it? So in order to look at that, let's go back to the data now. So we've done the data, we've seen the snail, we've done the mechanism. Now let's go back to the data and re-examine the snail and see what we can see. This is the Gaia data. So here's the Gaia data, the original visualization. This is a visualization of the Gaia data, a very similar data set. We flipped the axes just to make you think a little harder. And this is now the Z direction. The nice thing about this is it's easy to go, oh, we're going up and down because it's the Z direction, right? But it is flipped relative to the original Gaia data set. So that's why I'm showing you here. You have to flip it around and you actually see the same snail, okay? So this is still the Gaia data set, just re-visualized. And what I want you to think about is the mixing we talked about in terms of around the galaxy. In orange, as a function of galactocentric radius, this is the different radii that the disks, that the stars in this sample, and there's 4.5 million stars in this sample. This is the range of radii that they occupy, between 7 and 9 kpc. If, however, you ask what sort of orbits are they on, what are the guiding radii for those circular orbits around which the little epicycles are? If you estimate those for these stars, you actually see that these million stars that are now within this small range around the sun actually explore a much larger range of radii around the galactic disk, which is really fun. And this means they have a range of azimuthal time periods. These stars are going to go, if you go backwards in time, these stars would go further in azimuth than these stars in the same amount of time, right? So one fun thing we can do, therefore, is split this set of stars. The orange set and the blue set are the same thing. Let's split them up according to not the radius where they are now, but the radii of their guiding centers. And actually that's exactly equivalent to splitting them up according to their angular momenta. So if we do that, this is what you get. We're now looking at real data. Here's the real data, but we're splitting these 6.5 million stars into data sets, which each contain, these inner two contain 2.5, 1.5 million. This one contains just 25,000. So all of these stars are in this panel. And what you're seeing down here is if we look at those sets separately. And what I hope you can see is that the spiral that you see is systematically different across these panels, in particular this last one. The first one is starting, going up and then down and around. The second one, there's less of an up motion, going down and around. And the third one, you start at the center, there isn't even a center, you go down, whoops, I'm going the wrong way again. You go down and up and around. So in other words, you're seeing this one beautiful spiral pattern we see in the local data set, we can actually see hidden within it are several different spiral patterns. So actually, it was Shevin and I made the original visualization of this. And so this is showing you the Gaia data as an animation. You're zooming through systematically, going from the outer part of the disk to the inner part of the disk, different ranges in angular momenta. And I love this movie. You can really see how the spiral changes. I love this movie so much, you're going to have to watch it again. The amazing thing about this, the thing I really love about this movie, sorry, we're going the wrong way again, is this is real data. So you can see in this case, spirals going up and down, and then by the end, the spiral's going down and up. And sorry, but this visualization has the axes the other way again, just to make life really exciting. So this is really fun. Okay, so what can we do with this? We now know we can look at the local data set where we've got 10 million stars. We can split it up and we can actually, in effect, look at different parts of the galactic disk in the past. So in the last few minutes, I just want to show you where we've got to with this. We haven't got to the end of the story, I'm sorry. Here's the real data. Here's our test particle simulation. We found somewhere, this is not supposed to be a match, it's just supposed to be similar. We found a similar volume and a similar spiral in the test particle simulation. We can play the same game, and in that small volume, we can split it up, and similarly, we can see different spirals. But because this is a simulation, we can actually highlight those spirals, and we can ask, where did they come from? So now let's look at the stars. There's green stars and there's blue stars that have been highlighted in this small volume, but separated out according to their guiding radii, and then the peaks of the spirals. And this is showing you at this particular point in the simulation, this is the volume we were looking at. So the blue and the green stars are coinciding. This is as if we're doing a small local survey. This is the spiral that I highlighted, traced by the green particle in Z, VZ. And this is the spiral traced by the blue or cyan particles. And because we're looking at a simulation, we can look backwards. So we can say, where were these about during Sagittarius's last impact? And indeed, you can see that these were at systematically different locations in the disk. And you can also see that the spiral has rewound. It's not perfect, but you can see there's a systematic offset in velocity and in position. They're at more closer to a single phase, and they phase mixed from the time of impact forward. So the information that's contained in these panels, once you've rewound these spirals, should be telling us information about this galactic interaction. Okay, so I'm out of time. I promised to go short, but I'm still out of time. But this is everything I wanted to say. We haven't got as far as applying this to real data, but welcome to the Milky Way. I hope you've enjoyed a quick tour of some fundamental dynamical properties. And the takeaway is really that the Milky Way and Gaia is a great mechanism for learning about galactic dynamics. Thank you very much.
Thank you for a wonderful talk. It was really excellent. I enjoyed it myself very much. If you also enjoyed the talk, please say something in the Zoom chat. I will share the chat transcript with Professor Johnston at the end, or say something on the YouTube chat if you're watching on YouTube. For the question and answer session, it sometimes works a little better if you turn off screen sharing, so people see all of you. But if you feel like you want to go through the slides, you can leave the screen sharing on.
Yeah, I think I'll leave the screen sharing on in case questions come up.
If you want to ask a question in Zoom, please use the raise hand feature. If you want to ask a question on YouTube, please type it into the YouTube chat and it'll be passed to me by my associate. We already have one YouTube question that is preloaded. Maybe I can start with that one. So an anonymous question from YouTube is, to what extent are these different motions decoupled? Can the dynamics ever become chaotic or ergodic?
Oh yeah, that's a great question. So the first part of the question, they're largely decoupled, but they're not completely decoupled. So I think for small oscillations from the circular orbit, that's okay. An interesting signature of that is sort of, if you start looking at this, actually this has more to do with potential, but notice some of these spirals are not very circular and some are more circular. That has to do with sort of the shape of the potential and the degree to which you would expect some coupling, in other words. The question about ergodic and chaotic, right? So there's a whole other set of wonderful things coming about Gaia where you can actually look in the disk in the in-plane motions. I've concentrated mainly in the perpendicular motions. And in the in-plane motions, there are lots of beautiful signatures of resonances. And it is an exciting question. And these would be resonant interactions between the spiral arms and the local stars, or the bar and the local stars. And it is an interesting question of whether we would be able to detect signatures of chaos around those resonances. There's a whole other literature on that, which I didn't have a time to go into.
Okay, thank you very much. If there are more questions in Zoom, please raise your hand, or if there are questions on YouTube, please go ahead and enter them into the chat. I don't see any entering on YouTube yet, and I don't see any raised hands yet, but I'm sure there are people who have questions. There is one. So Hussein, please feel free to lower your hand, turn on your video if you like, unmute yourself and ask your question.
Hi, yep, thank you for the amazing talk. In the animation, something seems to happen towards the end, near like the z is equal to 0.
You mean this? Oh, the vertical feature here?
Yeah.
Yeah, no, I think that's an artifact, a data artifact. And don't ask me to explain it to you, but don't think of it as anything physically interesting.
Oh, okay.
Sorry. Yes.
Okay, if that's the end of the question, there's another one here from William Minerick, Doctor. William Minerick, Doctor, could you please unmute yourself and ask your question?
Sure, it's the default McGill title. My question is about the spirals. How long do the spirals persist? In other words, the galaxy has seen lots of mergers. Sagittarius is just the most recent. There should be spirals all over the place, or do they damp out?
Yeah, great question. So actually, there's one of your Canadian colleagues, Larry Widrow, has done some great work on this, led by a grad student, Darling. I don't know his first name. And they very carefully looked at both the sort of test particle simulations I'm showing you here and self-gravitating simulations. And so what they were finding in the self-gravitating simulations is Sagittarius itself is setting off a spiral, but then the disk goes up and down. And the disk going up and down is also a vertical perturbation, and that can set off spirals too. So actually what happens, I think what's going to happen is that the persistence of these spirals is not nearly as beautiful as what I've showed you here, which is why I'm hesitant to interpret the data yet. But the number of spirals is actually quite confusing, because now we've got Sagittarius setting off the spirals, but maybe also the vertical wobbling of the disk. And then secondly, another paper has been looking at when the bar forms at the center of the galaxy, that often forms by buckling, which is also a vertical motion, and that can set off spirals. So the answer to your question is it's complicated, but the beauty of the Gaia data set is the amazing amount of information we have, because this, remember, is just within a kiloparsec of the sun. And in the next data release, we're going to be able to do that in volumes like maybe tens of times that volume, which tens of times this much data or this many signals of spirals. So my hope is that we'll be able to disentangle those different origins using that.
Okay, thanks. I think there are many more questions now. So the next person is Professor Jim Klein. Jim, could you please unmute and ask your question?
Hi. If I'm not mistaken, these vertical motions are also used to constrain the possible existence of a dark disk. Is that right?
Yes.
Do you have any updates on those kind of constraints at all?
So honestly, this is we're gonna have to sort this out before we can get back to constraining the dark disk, because the dark disk is supposed to be much thinner than the I think the type of the dark disk could have various shapes, but one particular type of dark matter would give you a very, very thin dark disk. And what you're trying to find is the classic measurement is to measure the equilibrium structure of the stars as they go up and down with that dark disk. Now, if the whole thing has got a ripple in it that changes as a function of radius, then you're no longer in an equilibrium with the dark disk. And so that's going to be a little difficult to detect. Going back here, these interesting corners to these spirals are saying something about the gradient and the density as you go away. So it might be that at the very center here, if there's a dark disk embedded within here, your spiral structure should be more angular than it actually is. I'm to be honest, I'm kind of making things up a little bit to give you the sense of the sort of argument that one might be able to make. So I'm not saying my argument is correct, but those are the sorts of features you could look at. So I guess what I'm trying to say is the way you've tried to find a dark disk in the past, those methods, the fact that the disk is not in equilibrium, call into question those methods. Not that the disk is far from equilibrium, but it's sufficiently far that your sensitivity has gone down. You have to correct for it before you can be sure. However, as we're understanding what these diagrams look like and we're able to make them, the ZVZ diagrams, it's possible we may be able to come up with a different measure of trying to detect the dark disk that has less to do with that assumption of equilibrium in the first place. Whew. Does that make sense?
Yes, thank you.
Okay.
Okay, thanks a lot for the question. There's a question from the Zoom chat, and the question from the Zoom chat is, how long have single stars been followed?
Oh, yes. Compared to their orbits, an infinitesimal amount, right? But it is true, right? We have proper motions for 1 billion stars, but it's not around a significant fraction of the galaxy because that takes hundreds of millions of years. I'm not sure if that answers the question, but that's how
I'm not sure either. So questioner from the Zoom chat, if you have more questions, please load the chat
do.
with them
Yeah.
and I'll try to see if they can be addressed if we've got time. So the next question was from Professor Peter Gruder, who had his hand raised. I'm not sure if he still wants to ask. Peter, go ahead. Peter.
Hey, Kathryn, thanks very much for a great talk. I particularly appreciated the movie in the dynamics talk. So I have a question. I'm not an astronomer, so it might be a really stupid one. Does this dynamics actually affect planet formation at all on a much smaller scale than parsecs, which seems to be pretty large?
Yeah, no, so that's an interesting question. I think I think you answered your own question, that it's just the scales are just too different for this to be important for planet formation. Yeah, sorry.
Oh.
I apologize for that answer.
Okay, well, thanks a lot. It's good because it gives us more time for more questions, which we have. So the next question comes from Daryl Haggard. Professor Daryl Haggard, could you please unmute yourself?
For sure. Thank you very much. That was super fabulous. So I have a question about the data, and I realize that you're drawing a lot of inspiration from this really rich data set, but I know Gaia can also do proper motions across larger distances throughout the galaxy, sampling brighter stars. So you bring in a different suite of biases that way. But is there any thinking about whether or not you can use that larger, more distant data set to sort of start to piece out some of these dynamics over a larger range of radii in the galaxy?
Yeah, you're actually giving me an excuse to go back here and think about this, right? So if we go here, right, we talked about vertical oscillations across the whole disk, which Gaia indeed has mentioned, has mapped, right? But in a sense, right, you're completely correct. Each of these spirals has an average. If you averaged over the z direction, you get a mean VZ up or down. So if it was just Sagittarius and then some phase mixing, you get a relationship between this mean VZ and the phase of your spiral at each point in the disk. And so I think finding spirals in the more sparse data set is going to be hard. Gaia makes us think, well, the richness of the Gaia data sets allow us to see these very small departures from equilibrium. So they're not very, so if you have a small number of stars, because you're further from the sun in the data set, it's harder to pick up these small departures. On the other hand, you can measure the mean there. And what we should see is there should be a relationship between the phases of the spirals here and the mean oscillation up and down on a global scale. That's where I want to go in the long run, honestly. Currently, it's like you want to do a giant fit for everything all at once, including the microscopic and the macroscopic data set. I personally cannot get my head around that right now, but that's where I think we should be going. Does that make sense? Yeah.
Fantastic. Thanks. Yeah.
Well, thank you very much. I think we have time for one more question. We might squeeze in two, depending on how long it takes. So Emma McKay, could you please unmute yourself and ask your question?
Hi, Kathryn. Thanks for a lovely talk. You might have seen the most recent issue of Nature Astronomy dealt with the climate impact of astronomical pursuits. And I'm wondering, since Gaia was launched by a rocket into space and is made of metals that were taken from the Earth, do you have any sense of the climate and larger socio-environmental impact of your research?
I think that is a great question, and I do not know the answer to that question, and I have not read the latest issue of Nature. So I think that we as a field are just learning that we need to think harder about these issues. My hope would be that something, but of course I'm biased, my hope would be that the human race collectively would be able to prioritize, and we'd still be able to send some research missions up there and prioritize that along with everything else and come into a balance. But I need to look at the current version of Nature to inform myself better. Thanks for bringing it up.
Okay, thank you for the question. Please lower your hand if you're done. And the last question of the evening will come from Mohit Bardwaj. Please unmute yourself and ask your question.
Hello. First of all, thanks so much for the talk. I thoroughly enjoyed it. So I have a question related to H2 regions, galactic H2 regions. I think it was previously proposed that giant H2 regions, supernova remnants, or strong X-ray features like Fermi bubbles may also affect the dynamics of stars, at least in the local neighborhood. I'm just wondering if we can test this using Gaia data, or at least see the systematic offset in velocities like what you have seen in the case of Sagittarius galaxy merger. That's all. Thank you.
No, that's very interesting. Yeah, the nice thing about Gaia is it allows you to dream, right? So you could dream if you can know where an H2 region is in the galaxy, the giant ones, and you can find the center of it, find the center of your bubble. Maybe you can do something with seeing if there's systematic, do a filter where you look at systematic motions in the radial direction or something like that. I could imagine you putting, with the number of stars we have in Gaia, the bright ones, I can imagine you trying to do an experiment like that and seeing if there was a deviation from what you'd expect for a random distribution. I haven't heard of anybody trying to do that. Sounds like you should go and download some Gaia data.
Okay, well, thank you for the question. Yeah, thanks Thank you for the question. And let's all thank Professor Johnston once again for a fantastic talk, a very interesting and very good pedagogical talk. Great for a colloquium, I thought. Please write something in the Zoom chat if you haven't already done so, if you're in the Zoom session, or write something in the YouTube chat if you haven't already done so. Professor Johnston will be able to look at the YouTube chat at the end, the replay, and I will send her the chat transcript from Zoom. So that concludes this edition of the Physical Society Colloquium. Before we end the live stream, I would just like to remind everyone without a tenured or tenure track position in the Zoom session that they are welcome to join us at the Après Colloque to get to know Professor Johnston better. I won't be there, but others will. Please also join us again next week at the same time for a special Physical Society Colloquium co-organized with the McGill Graduate Association of Physics Students and GAPS. The talk will be given by Professor Sean Carroll from Caltech, and the title of the talk is From Quantum Mechanics to Space-Time. Thanks once again to all who have joined us. Good evening et bonne soirée.
Oh.